long time ago, I was at an ACI conference, and there was a session for professors that teach reinforced concrete. And I went to that, and I think it was Andrew Scanlon from Penn State. He got up and said that the hardest thing to teach in that class was this concept of where to cut the bars off, and I agree. And to help with that, I've come up with a mnemonic. So this is something that I've made up. And so if you try to tell somebody that hasn't had this class from me about it, you have to explain what you're talking about. It's H.E.L.P, and it's have any extra bars. And if it was just extra bars, then it would be H.E.L.P, and it wouldn't spell anything. So have any extra bars. Establish where the extra bars are no longer needed. LD for development length. And P, practical continuity details, the details that are in the ACI 318 code. So H.E.L.P, have any extra bars, establish where to cut them, LD, and practical continuity details. H, have any extra bars. This is the whole motivation for this. If you have lots of bars, you want to cut them. You don't want them going across the whole beam, particularly the negative moment steel. If you can cut off some of the steel in the top of the beam, it makes it easier to pour the concrete into the form. Also, the bars that you're not cutting, you need to know how long those are, but we are also looking at, this is what makes it hard, do you have any extra bars? And what I like to do is, as you take bars out, I like to maintain symmetry. And this is the whole concept of what we're doing. So once you've decided that you do have extra bars, then you need to establish where those extra bars are no longer needed. You need to locate the theoretical cutoff points, that is, where you no longer need the bars. So for example, if you had a beam like this and it had 4 bars in it, you could cut 2 of them out. I'm just gonna make up some numbers. Let's say phi mn was 100 foot kips, and then phi mn here was like 51 foot kips. When the moment diagram gets down to 51 foot kips and below, you could have only 2 bars. And so what you need to do is find where on your moment diagram this 51 foot kips would be. But you're not allowed to cut right there. You have to extend past this point, D or 12 bar diameters, because things are never what you want. The exception to this, so the 2 exceptions are, so theoretically you don't need those bars once it's 0, but it's silly, right? You can't extend that bar an extra D past the end of the beam. It'll be out in the air. That doesn't make any sense. Okay, so that's the exception to that. You have to say stuff like that, or people will apply the code blindly. LD. So use the appropriate development length equation from the code. We spent several lectures talking about the behavior of bond and where the development length equation comes from and how to use it. This is just a small part of this whole process of determining where to cut the bars off. You need to make sure that wherever you're cutting the bars, from there to where you need them is at least LD. And we'll talk about this in an example. Okay, practical ACI details. So in general, in 9.7.3, 9.7.3.1, so that's what all these numbers are. They're the subsection numbers. So 9731, 9732, etc. 9.7.3.1 says that you need to develop on both sides of a section, the bars. And so what that means, if you had a situation like this, you need to develop on that side, and you need to develop on this side. You have to have the hook development length long enough, and you have to have the straight bar development length long enough. The critical points that you need to check are maximum stress and where you cut the bars. Anywhere you think you can stop the bars, you have to go an extra D or 12 bar diameters, whichever is greater, except of course at the end of a cantilever or a simply supported beam. Right? You end there. You cannot extend. We talked about this. You cannot extend that bar out into the air. And then finally, the continuing bars, the bars that are not cut, must extend LD past the theoretical cutoff point of the cut bars. That's a little hard to explain. I'll make a separate video just for this topic, and so we can talk about that in more detail. Okay. Next slide. This also gets its own special video. Cutting bars in tension affects the shear strength of the beam. And when a bar is in tension, and the bars are usually in tension, right? That's where you put the bars. If you cut them, you have to meet one of these three requirements. We'll talk more about this in a separate video. And then the code talks about tapered beams and bars that are bent from the bottom to top faces. You have bars up there, you have bars down here. You can make them the same bar and bend them up like that. Not a typical practice, I think, here in the US, but it is done. So the code talks about that. We won't cover that in this class. And then there are more of these practical details that have to do with positive moment. And so if you have a simply supported beam, 1/3 of your steel has to go from support to support. So 1/3 of your steel has to go from one support to the other support. Okay, so that means you cannot cut more than 2/3. Okay. And if it's continuous, so there's steel that goes like this, and that moment diagram looks like this. You only need the positive steel where there's positive moment, but it doesn't matter. 1/4 of the steel has to go all the way across the span, no matter what. And this comes from experience. These kinds of continuity details help the beam stay together and perform well. Okay, this one's a little complicated. At inflection points, so that means wherever m equals 0. So at inflection points, so at a simple support or where the moment crosses over to 0, you limit the development length. The development length has to be less than this. Or if you have a compressive confinement reaction, this. Let me explain where this comes from and then come back to it. Okay, and so remember how we talked about the strength increases from 0 to the full strength over the development length. So if let me draw this. If this was the capacity, it takes LD to get to the full capacity, from 0 to the full capacity over LD. And so you don't want this to happen. So the beam is strong enough over there, but it takes so long for the beam to get up to its strength, it goes below the moment diagram. And that's no good right there. So how do you prevent that from happening? It has to be tangent right here. Does that make sense? If it's tangent right at the start, because this curve is bending over, it'll always be outside. And so what we need is the slope of this capacity diagram. We need that slope to be steeper than the slope of the moment diagram. And from elementary structures, you know that the slope of the moment diagram is the shear. Okay, so right here, this slope is VU, and the slope of the other diagram is MN over L. So you need MN over L needs to be steeper than VU. And if you solve that for L, you get this. So the development length needs to be less than MN divided by VU. And that makes this happen. Okay, so now let's go back to the ACI requirement. So there it is. L less than MN over VU. So what is this? Okay, so here's a beam. There's your moment diagram. There's that MN over VU slope. Okay. And it needs to be outside. But you see this bar? It doesn't stop at the support. It goes all the way past the support. And this extra length is L additional, or LA. And so you get to make it easier for the development length. The development length needs to be less than that big amount there. Okay. Now, here, this thing here, let me try to draw this again. So here's that beam, and this support is pushing up on the beam. And what that does, it's increasing the friction, right? So if you're pushing on something, it's harder to slide out. And so it'll give you more bond, and you can have a shorter development length. And so you get that bonus here. For example, where you would not use that, if you had some kind of weird thing like this, I don't know why you would do something like that. Okay, and so this reaction is on the top in tension, which would be a bad idea. There's no compression on that bar. So you usually do get this 1.3 additional bonus. Okay, now there is one practical ACI detail for negative moment, and 1/3 of your negative moment steel has to go past the inflection point D 12 bar diameters or L over 16. So that's this. So here's your moment diagram. Okay, so when the moment changes from negative to positive, that's the inflection point. You could stop the negative moment steel, except you need to go an extra D or 12 bar diameters. That's always the case. But for negative moment, you also have to check, it has to go an additional L over 16 past there, the greatest of those three. And that sums up all the practical ACI requirements. Let's try a little example and walk through it, what all these things mean. And we're going to do this. Help. H. Have any extra bars? It's sort of like have milk. Okay, so got milk. So have any extra bars? And know, if I said, do you have any extra bars, then it would spell delp, and it wouldn't be a word. So have extra bars is H. Okay, so here we have 4 bars. You could take out 2 in the middle, this one right here. I personally don't like taking out 1 bar because I don't like things to be unsymmetric. 3 bars, you could take out the middle one. 5 bars, you have 2, actually you have 3 options, right? Good. Take out the middle 3, take out 2 of them. Another option is you could take out the middle bar, so you would have 4 bars left. And in all cases, we've not taken out more than 3/4 of a bar. Remember, you have to have 1/4 of the bars going all the way across. 2 bars, there's nothing to cut, right? 2 bars just stays at 2 bars. And this is the one you really want to do. If you have 4 bars on the top for negative moment, you do want to try and get rid of 2 of the bars, so then it's easier to place the concrete from the top. And you need to keep 2 bars at all times because they help in the cage construction for the stirrup. So do you have extra bars? Just decide how many you can cut off. Okay. Establish where you no longer need them. Okay. So this beam has been properly designed. So here is, I can't see that. That is 203 foot kips. And somebody designed it to have 209, so it's fine. When you take out 2 of the bars, you go down to 122. Okay, you do T equals C, solve for A, Z is D minus A over 2, Mn is T times Z, Phi Mn is 122 foot kips. What you do is you find 122 foot kips, you come across, and you find where on your moment diagram you have 122 foot kips. And by the way, the moment diagram is a parabola, right? Because, you know, if W is constant, shear is linear, and moment is parabola. And parabolas are symmetric about their maximum. If you think about it, right? That's what a parabola is. And so it will be symmetric around the maximum. And so this here and that there is 122 foot kips on the moment diagram. That's theoretically where you want to cut them, but what you have to do is go an extra, and we call that proposed cutoff, because you still have to check the development, right? So we're going to propose cutting it off an extra D or 12 bar diameters extra to be safe. Now, the question is, let me erase that real quickly. How did I know to go out that way and not come in this way? Right, so let me switch to the pen. Well, that's not safe. You're making the bar shorter, right? It's definite. You need to make the bar longer to go outside of that moment diagram. Okay, and so that's P. So you would do a similar thing here. Let me move myself out of here. This is 155. Oops, get the pen right. That's 155. Greater than this 150. We'd have to find 98. So someplace over here. That would be 98. And then you would have to add outside of that D or 12 bar diameter. So again, this is theoretically where you would cut it, and this is where you're proposing to cut it. And next, you have to check LD. So development length L. Okay. And this is what we spent all those lectures developing. This will tell you, remember, this is LD divided by bar diameter. So it'll be this number that you calculate times the bar diameter. So you calculate the development length. Once you have that development length, the next thing you do is you come back to here, and you need to verify, let me change the color, green, that where you're proposing to cut it off to where the maximum is, that has to be greater than LD. That has to be greater than LD. Okay? And we'll check this in an example. And then finally, you have these practical continuity details. That's the last step. Oh, there we go. You need to check, did 1/3 of the steel, does 1/3 of the steel go all the way across? Okay. You need to check, is that to the maximum greater than LD? You also need to check from there to the theoretical where it was going to cut the bars. Is that greater than LD? And I'll have a separate video just explaining this LD check, but we need to do that. And then finally, and I'll have a separate video for this, if these bars are in tension, and they are, you need to verify that 0.5 code. Let me go find the words for that. Need to verify this. Oops. Okay, you need to verify that, and I'll have a separate video for that. So you have to check that the LDs, and you have to check this, and I'll have one separate video for both of those. Okay, so that is my little mnemonic to do this process. H.E.L.P. Help. Have any extra bars. Establish where those extra bars are no longer needed. Calculate LD and check. And finally, all these practical ACI details. Okay, that's that. And so again, another video just on how to check the LD, and another video on those tension check cuts.